Good afternoon, guys, and welcome to the Industry IoT Virtual Workshop Series. As you guys know, today we have Gunther Beitinger, who is a VP of Manufacturing at Siemens Digital Factory Division. Welcome, Gunther.
Welcome, and thank you. Thank you for inviting me, Daniel.
Absolute pleasure to have you on board. I'll keep my bit brief. Gunther's going to do a quick presentation for us, as you can see, about factory automation, speak about some of the requirements and challenges of a smart factory, and also touch on predictive data analytics as a precondition for a smart factory setup. What we will try and do is split the session into two parts, the presentation and an interactive Q&A to follow. That said, at any point there is an interactive Q&A chat room. You guys can post questions and Gunther can answer them as we go. I hope you can all see and hear us okay. If not, please make me aware. But that's it from me, and Gunther, over to you.
Thank you for the introduction, Daniel, and also from my side, a warm welcome to our webinar. After I have spoken with Daniel, I decided to have mainly three parts in my presentation. The first is a small introduction of what we are doing and what are our challenges. The next part would be we are working currently on our Lean Digital roadmap, which should give a very interesting insight of what we are working on and what we are foresee for the future. And then in the last part, I will go a little bit deeper in that data analytics and predictive data analytics topic to see what we have gained so far from this special, let's say, topic. Let me start first. Does it work? Let me see now. It doesn't switch my slide now. Okay.
There we go.
There we go. Yeah. So, so I'm from the division Digital Factory. For the ones who are not familiar with the Siemens organization, here's a short introduction to it. We are organized in so-called divisions. Here you see the different areas: power and gas, power generation services, energy management, building technologies, mobility, process industries and drive, Siemens Healthineers and Siemens Gamesa renewable energy, and of course the services area. And I'm from the division Digital Factory. Our products are normally well known in the automation area and automation sector. We do PLCs, programmable logical controllers for factory automation, also control products for switch gears and for short breakers. And we also have the CNC controls for machine and motion control. And of course, we are also providing the software for our hardware. And beside of this, we're doing customer services. So the challenges for us when we are talking in spite of our own factories, so not what we are providing now directly to our customers, but also that what we are providing and what we want for our customers, we are also have this as our own challenges in our own factories. We are talking about perfection for our customers, what we also would gain in our own factories. So our strategy has 6 pillars. Definitely, we want to drive digital enterprise. We would like to produce world-class products. We have strategic, holistic partnerships with our customers and with our suppliers. We are looking for global added value and competitiveness. We are having our factories in all marketplaces, in the 3 big markets, Asia, Europe, and Americas. Of course, we are looking for highest quality and efficiency. and we are challenging us with our social responsibility and ownership culture. This is what we are aiming for. This is our vision and mission, and this is what we are dedicating our strategy. When we are looking for the challenges of the future, I think everybody can agree that if you are running factories, you're looking for speed regarding of time to market, bringing products to the market. So you're thinking about reducing throughput time. You're looking for flexibility. You have high variance in your factories, volatility in order income. So what you're looking for is agility, flexibility in your factories due to the volatile order income or to the variety of products you have to produce. Of course, you look for highest quality, and beside of this, you have to reduce costs. So you have to be each year more efficient than the year before. Of course, by doing this, we are driving new business models, and we want to do this in a secure, especially with the data and big data topic now, in a secure environment that you do not have to fear intruders from outside, and you can produce your products in an environment which allows you to assure to your customer that the software or the firmware which are in your products are also really is what is in your product and nothing else. So this is a short introduction, and everything else I would like to show you a short video now. Let me start the video now.
Each of us is unique, which is why we all strive for individuality. We want personalized clothing, food, and services, and we want to receive these custom products as quickly and easily as we get all other mass-produced products. Individual needs become individual challenges for the manufacturing industry. To continue meeting customer requirements in the future, companies have to shorten their time to market and manufacture products more flexibly than ever before. Products have to be of higher and higher quality, and ideally be produced economically and without harming the environment. Moreover, companies and customers want to benefit from new business models, and they must meet all of these challenges while complying with the strictest security standards. But how can you adapt your production to constantly changing market requirements and still remain competitive? With a holistically integrated and digitalized value chain from product design and engineering to the real production and service. With a digitalized product design, you get a digital twin of your product, which is linked to production planning. This is where you digitally plan your plant or machine, and with this digital twin of the production, you'll optimize production, ergonomics, and much more. With virtual commissioning, you can streamline your production processes during engineering, and in the next step, turn your digital plant into reality with the greatest possible efficiency. During actual operations, the digital twin of performance is created. It gives you more ways to optimize in order, for example, to increase the availability of your machines. You generate data during operation. With MindSphere, you analyze this data and gain insights into resource consumption, predictive maintenance work, process stability, and much more. Let this information and a lot more flow back into your value chain in order to establish a continuous optimization process. This integrated and digitalized value chain gives you an image, a digital twin of your product, your production, and your performance. You can begin at any point in the value chain, individually tailored to your specific needs. Here in Hamburg, we have optimized our production according to this same principle. Today, we are able to manufacture more than 60,000 products in 120 different variants. all in a single day and at top quality. Welcome to the highly efficient Amberg factory. Siemens, ingenuity.
So I showed you this video because it shows also our, let's say, fleet plant, where also I have my office of Amberg, and what are the challenges and what we are currently working on. And to give you now a little bit more of these insights regarding how we are really would like to implement our vision to become a lean digital factory, I would like to introduce you to our, let's say, roadmap project, which is, I think, very interesting for people who really would like to bring their operation to the next level. When we started the digitalization roadmap, we saw that over the last years, the classic, we call it classical productivity measures, are very difficult after a certain time to assure 3 to 5% productivity in our plants, even that all our plants already are on a good level regarding lean production and lean administration. We saw this due to the fact that in 2010-11, we had only 1/3 of the measures we have today to assure the same amount of productivity. And this was a clear sign it will get harder and harder in the future to keep up productivity in our plants if we are not starting really to use and implement a higher degree of automation and also really take advantage of all the possibilities digitalization is offering. But for this, we need a structured approach. So we started let's say, the definition of a lean digital roadmap for all our 22 plants. I'm heading this project, and you see here where we have all our plants and how we are organized this over 5 work streams. So we implemented 5 work streams accordingly to some technology, or let's say technology cluster aspects. I will come later a little bit more in detail, but I named them here up front. So we have a technology cluster which is called disruptive technologies, which are dealing with increased productivity through automation and digitalization. We called one content cluster with streamlined PLM. Here we would like to work out shorter lead times for product development and for our production introduction. We had a content cluster which is called end-to-end. Here also shorter the lead times from customer order to delivery. By the way, with less inventories and also with less full-time equivalents or headcounts. We had named one IoT operating system to drive increased OEE, overall equipment efficiency, and one cluster which is called people and methods, because we also have to deal with our implemented workforce. What do we have to do to get them on board, and of course what can we do to make them adaptable to all the challenges which are coming in front of them. Avoidance of duplication of work is also a point of this. So we started, of course, with some technology workshops. We looked of that, what we are doing in all our 22 plants, because we had independent and separately roadmaps, or let's say strategy implemented. And then we also looked outside with innovative companies. We were looking to universities and were getting a good overview of that. What is at the moment possible in technologies, what our people are looking for, and what our universities or high innovative companies are developing at the moment. So we had then a good overview of all the technologies we called, let's say, which are interesting for us, or had the potential to change the way we produce in the future in a drastic or radical way. Then out of these, we defined a so-called reference processes. So we went into our plants, we mapped our processes in all the plants, and out of these we developed a future state, a future reference process design, which showed us where do we want to be by 2022 and 2023 in regarding of the digitalization aspects. And we worked out so-called technology radars to see the maturity of the technologies when they will be available. And by the way, also, of course, we mapped our software platforms. This we worked into so-called digitalization roadmaps with the 5 content clusters. And then out of these, we were working then out the IT roadmap. So what is the target architecture for the future to make, to be sure that we can use all the new possibilities, especially in kinds of data analytics or in data throughput through our systems. And what we are doing right now is, of course, we are defining the right software for our use cases and for the functionalities we have defined. Let's go a little bit deeper here. So you see one process mapping, especially digitalization roadmaps, was derived from our reference processes. We went into our factories, we mapped the, let's say, core processes, and we had a deep process design out of this, and then derived the IT architecture. And then also in the latest point, we estimated what will be the impact in regards of time, in regards of efficiency or costs, and in effort to, let's say, avoid effort. And then we also saw the impact and the costs related to it. This is an example of a reference process we mapped, that you have an idea. Here we mapped the reference process production system planning. So how do we want to get our production systems in the future planned? And what I would like to show you with this is we had a really detailed future map here, which this is only 1/3 of the map we defined. And we said, okay, everything which has no red dot, this will be done in the future completely automatically without any interruption or manual interference. And only if there is an exception in the process, we are then a manual interruption will be necessary. And so we had we had an estimation of that, what is the potential by digitalization of process in aspect of that, how we are doing it today. And then out of these, of course, together we are defined the roadmaps. Here, the roadmap Lean Digital Factory Module Streamline, PLM, Product Lifecycle Management, and as you have heard it in the video, we want to address the digital twin here. So how you can read this roadmap? First of all, we defined a target state. For example, we would like a product 100% digitally described and in real time accessible. For this, we need to have a digital twin of the product. But what does this mean in our environment? We need a full product manufacturing information of this product. And then we need to have full design rules and quality checks implemented. And at the end, we need a full comprehensive description of the product. On the other hand, when we are talking about a digital twin of production, we would like to get to a target state that we have an integrated digital twin of product and production in real time, where the production is described totally and first time right in hardware and digital continuous improvement projects. This means we have to do our digital process simulation for all our processes. Then, of course, we have to derive a holistic value stream, and also in real time, out from the simulation in real time. And then we have a comprehensive description of our production. And out of this, of course, then you come to the digital twin of performance, where you are able to have a real-time controlling of production via the digital twin of performance, by having all relevant data of real production available by a click. And you are then able to have analytics based on this performance optimization. And at the end, you can use artificial intelligence or other rule-based decisions out of data analytics. And how do we get there? This is how the 14 dots on the right side you see. These are so-called project clusters, where we are describing what we have to do to get to this single evaluation states. And also we have then a map in which plant we are doing which project to come to this target or to the intermediate evaluation states. So this was, for example, one module. And here in the next process end to end, you can see how we mapped our future inbound and intralogistics process by using a full digital twin. We saw, okay, the production comes in, and then before we are ordering, or let's say make the release for production, we are simulating these in the digital twin if we have all necessary capacities in place by machine, by people, and by material. And if this is given, then an automatic production release is possible. And this is only then without any manual interference possible if you have a complete digital twin of performance in your plant. So how to get there is also shown here. We have a target state defined, for example, the decentralized self-regulating and self-optimizing system steering complete the supply chain. And for this, we need the cyber-physical systems and self-learning systems. And how do we get there? Of course, first, we need that the product are communicating with equipments, and then the equipment communicates with each other, and then back and forth closed loop communication is possible. So you can see how we are getting from one state to another, how is the evaluation states are developed. Or for example, for self-learning systems, we need system alerted automatically, and then system provides solution, and then system decides with artificial intelligence. And also shown here in this roadmap is the other trend, the transparency across supply chain and digital consistency for getting to the target state that the complete supply chain digitally is connected and optimizes efficiently based on real time. And for this, data exchange platform across supply chain is enabled. Extended data traffic to all relevant data types is possible, and then you get to the system is deciding with the support of artificial intelligence. Another trend, agile intelligent decision making, is done here on the right side, and also the same logic behind. And when you see on the right side, again, these are the projects which are behind of it, who will assure that we are reaching the evaluation states. The next work stream is the Internet of Things. The trends we identified for our plants which are important is cloud computing, one comprehensive and secure data lake for relevant data. And for these, you see how we will get there. The production assets are fully connected to the cloud, and then the ERP, PDM, and MOM platforms are getting connected to the cloud, and then also the processing in the cloud is possible. Tracking and tracing, traceability is a very important topic for us. Also, the full traceability roadmap is shown here. So overall supply chain traceability is established at the end of this 21 roadmap here, and again the analytics and artificial intelligence, how we will get and you get full potential out of this is, first of all, we describe the processes, we have prescriptive processes established, and then the pattern visualization, and then pattern recognition and proposal available. And also I will show you where we are here in this aspect, especially because it's one of a very interesting area where you can get and gain a lot of productivity and reduction of efforts, especially in quality. I show you now the next work stream. Here, disruptive technologies. The most of the people have heard about disruptive technologies. This is, we call disruptive technologies here in the context, all the technologies who have the potential to change the way how we produce today. So it is not totally aligned with the disruptive idea as you heard. It is okay for us when it has the potential to change the way we produce in our factories as today. For this is we have advanced manufacturing. Beside of 3D printing, we also are looking for high pulse laser for subtractive and multi-purpose manufacturing. What is the idea here behind? Of course, we would like to realize economical production of batch size 1. And when you're going for such a target, then you do not want to have any changeover efforts. So you're looking for tools or for technologies where you do not have to do any changeovers. You can produce any variant of a product immediately without any downtimes due to changing of tools. And this is why we are looking for 3D printing of laser technology or for other technologies who are realizing changeover time of 0. So autonomous and intelligent transportation systems, a very interesting topic due to the economic availability of such systems, and of course due to the new functions they are offering. So the autonomous intelligent transportation are necessary in combination with collaborative robots to come to so-called robot farms with swarm intelligence. And when you have robot farms with swarm intelligence, you can, let's say, create full flexible and very, in a very agile way, production cells accordingly to the product you're receiving from your customer, and you are in a high flexible and agile way possible to use your workforce efficiently. So then virtual and fast production planning via using of virtual reality and augmented reality is very interesting in for learning and for quality aspects here. So coming to people and methods, our module where we are thinking about how we can take our installed workforce with us. So the people in our plants, for example, are people with high experience, but you need also to bring digitalization and a new way of working closer to them. So what we are doing on this side, we make digitalization for them understandable, and we are looking for new job profiles in regarding of the future of the competences we need, and therefore we are looking for that, what we have to do with new employees, but also with elder ones, and how we can make them the challenges, what they are aiming in the future, more or less fearable, let's say. For this also cross-functional agile working is our target, flexible collaboration, solution-oriented team settled, flexible pooling, and we would like to install even crowd working inside of our company. And of course, the digital guidance topic where we have online training aspects here with digital guidance directly on the office or on the shop floor. And this is now our future roadmap where we are going to be in 2022. And accordingly to that, what you have seen, these are pulling a so-called IT roadmap. And you see what this means, an IT roadmap. First of all, we have to think about all the data sources we are having in our complete company. So of course, we have the different data in different data sources. We have to bring them up to a consolidation layer. If we do not have them in a consolidation layer, then we are not having a central access and we are not able to take advantage of all the data for analytics or for centralized dashboarding or for whatever you want to do with them. So also here we have to rethink our actual IT structure, or let's say to adapt to that what we want to have in the future in regarding of the data utilization. Now we are when we have the IT structure, of course we are looking now for the right software which are bringing the functionalities we need with it, and for this we also are having a so-called evaluation for the software packages we are looking at. And this means we are looking for them, are they aligned with our roadmap or not, or do we have to make some customization with this software or with this software packages. And this is now our roadmap, what we are worked out. So it is a three-dimensional digital roadmap. It has the technology aspect, it has the IT architecture aspect, and also the software aspect in it. And this is what we are working on. So this is what I would like to show, that you understand what we are doing at the moment and how we are shaping our plans for the future. And now I would like to give you some examples out of the world of data analytics. And for this, I have prepared a few slides which shows where we are coming also again from and where we want to be. So when we are talking about analytics, is the overall question is here, so how can we become a smart factory? The normal way is you come from descriptive analytics. It is the status quo in the most of the plants. It's the ability to measure. Without measuring anything, you do not have data, and without data, you're just a person with another opinion, someone said. So you have data to be able to control, at least in a certain way. But if you would like to define action based on the measured data, you are addressing only the symptoms. So for this, the next step is you are analyzing that what you are measure. And for that, you have to evolve your interpretation ability. This is normally also in the most of the plants, the status quo. We can use Six Sigma here or Ishikawa or whatever to analyze that what we have measured, to come to root cause problems or root cause analysis, but still you are addressing the past. When you would like to get even further, now using all the data you have to predict, then you are talking about maybe pattern recognition, and then you are talking about predictive analytics, and then you have to train your prognosis ability, and then you come later to the prescriptive analytics, where you can even define decisions upon that what you have prognosed, let's say. And then all these you feed back in your development circle, and you're getting then better and better, and you build up your smart factory. When we are looking on the hot topics for predictive analytics in manufacturing, we normally have four typical areas. This is demand forecasting, quality improvement, machine utilization, and predictive maintenance. I would like to give you some examples out of quality improvement, which is very interesting in regards what you can realize here. We are coming out of electronic production. In electronic production, the X-ray testing is normally a bottleneck. So X-ray you're doing because you have connectors, like in this example, and the connectors are of course, then soldered via your normal SMD line or normal reflow solder process. But due to the fact that these are connectors and the pins are in the printed circuit board, you're not able to test them via a normal optical inspection system. You need to have an X-ray tester, and you look even behind the normal connector. You would like to see if you have a secure and safe connection. But X-ray testers are very, very expensive and very, very slow. So the idea was, can we define the quality upon the process parameters which are upfront in our SMD line? So the idea is simple. Is there a pattern who shows us definitely that this connector is absolutely okay and you do not have to bring them to the X-ray tester? And if you are not sure if it is okay, then you look at it. But if you find a pattern who tells you definitely if you are okay, then you do not have to test. And so we are started to collect data, to deploy data, and then we also find algorithms, and we find out that we can skip 42% of our X-ray testing only by data analytics, by recognition of a pattern of a process patterns. And just imagine if you can skip 42% of your test efforts. So here, for this, we are connected via an IoT 2040, for example. This is a small a box who collects the data out of your line. And so the data input in this example were 52 million data sets. We feed them into here into the cloud, or you can also feed them on a data lake, but you have to bring them also together. Then you are via analytics models on you can do this on the edge or in the cloud. You analyze your data, and then you see, okay, via the algorithms you have, let's say, worked out before, if you have to test or not. And like I said, what we have found out at the moment, at the first try, we could already skip 42%. Here you can see it, what we saw. We tested it, the true result and the predicted result is here absolutely impressive. And the slip of 2, where we had a false result, but the predicted result said passed, we say, yeah, this is something we might have to work on, but now we don't have even, we don't even know if we have a slip, because it's someone, a person who are checking this, they are looking at an X-ray picture, and then they are deciding. So we don't even have an information what is our actual slip at the moment. So this is why we can live with this, and we are working on this, how to get even to a higher output. And you see also what we have used. We have gradient boosted trees with meter cost algorithms used. I think this is for us a very impressive result, because we're talking here really about 6-digit number of savings. Another very hot topic for us in predictive analytics is the machine utilization, of course. We would like to get the overall equipment efficiency from all our factories. For this, it is interesting that we are connecting our machines or our systems to the cloud. We're doing this via this IoT 2040. We have a standard connection here. We are bringing up the data. If it is, we just look on this if the material is blocked or is not going out of a machine. So you know, okay, this machine is not producing, you have a downtime, then it registers the downtime, then we are feeding the quality aspect to it, and then we can calculate the OEE. Very simple and very effective. And then also regarding predictive maintenance, another use case. We have a full automated logistics system, which means really no one are bringing any material to our working stations. We are delivering the material directly to each working station without any manual transport. So for this, we have a full automated warehouse, and here the carrier systems are in this logistics systems are can get word out by the chain. So as you see in the second picture, so when they are picking or bringing boxes into the logistics system, by the time the chains here are getting worn out, and this is shown due to elongation or to the offset of the chain. And this can happen. This happens very, very seldom, but if it happens, then you have a downtime in our full automated warehouse system, and then no one gets material. And this is why for us it is critical, but the possibility is low, but when it happens, is critical. Now, what we want to have is that we are measuring this elongation of the chain, and if it is getting to a critical point, then that we are immediately react and exchange this chain. And this means we are measuring the time offset. So when the motor starts to move the chain, and there is a time set off between the motor, when the motor moves and the chain moves, then you see, oh, there is something going wrong, and then immediately you can react. And we have then the probability to react in time without any downtime of our logistic system. So also an example. What have all these three topics in common? When we're talking about data analytics, we say the common thing is here that the principal data mining setup is always following the same process. We call it the cross-industry standard process for data mining. This is where we are following. So first of all, if you're looking at if you have a use case, if you would like to say for which areas is data analytics the right thing, then you're thinking about your business or your process. So it's the key that you have your domain experts with you, and that they have really a process understanding. And you bring them together with people with data understanding. Why you do this? Because you need to be sure that the data you generate out of the process are really describing the process. Otherwise, the data are not usable for the prediction you would like to have. So these two people have to work out if the data we generate are really describing the process, and do we really understand the process in regards of the data we generate. And then after this, there might be a data preparation phase required, that you are maybe say, okay, I missed some data, I have to put in some additional sensors, or the data are not in the right format, or not in the right dimension. So you have to work on the data, and then when you have done this, you start to model. And then, of course, while you're modeling, maybe there is some additional data preparation required. And then you go into evaluation. And if you're going into evaluation and you have said, okay, now what I have evaluated, does this really make sense? And this is where the domain experts come again into the game. And then you give them back to your key experts and say, makes the sense, and then yeah, it looks good. And then if you have then the confirmation, you can go into the deployment as we have shown it to you, as I have shown it to you here. And then if you have the deployment, you can implement it, and then you have the possibility to get high impacts on effort reduction or on productivity. We have done it differently in the beginning. We just had data and we gave it to people without process understanding, because sometimes you hear this, hey, I have data. The other says, hey, I can analyze them. We didn't have any results with such approach. Now we are only doing this approach where we are bringing the data scientists and the domain experts together. And with this approach, we have now really good results regarding the projects we have started. So of course, then you can bring them into the cloud, and you can dashboarding your results or your analytics in the cloud. And this is a little bit our picture where we are going for. Of course, we have then the connectivity layer on the shop floor, on the physical equipment. We're going into this pre-processing data models, like I showed to you, and then you are bringing them into the next level for dashboarding or for data mining or for analytics. You bring them back into your production via the digital twin and feed it back, and you have a closed loop implementation. So this was what I wanted to show to you. I thank you very much for your attention. I hope you found it interesting. And now I'm, of course, available for questions. And yeah.